Hello and welcome to the latest video of heat transfer where we're going to talk about something really cool called similarity. Something that, to me at least, is really counterintuitive, but also really powerful. So we're going to talk about the experimental power of similarity. So you've heard me talk about before how for uh, conduction, our models actually work really well in terms of predicting reality. Convection is a whole lot harder. We went through some of the equations behind conduction. We would have to solve all of those equations all at the same time. We'll see what those look like a little bit down here. Convection is really hard. So similarity gives us an experimental way to think about and to actually do experiments on convection, on convection. All right, so let's pretend you're engineers. We don't have to pretend you are. Okay, so you're engineers. Let's pretend you're thinking about this system here. All right, so what do you have? You have a kind of goofy shaped little wing thingy. Say this is part of um, a hydrogen combustion turbine. So your gas over here is hydrogen. It's at 2 atmospheres of pressure, so not super high pressure. It's at very low temperature, minus 30 degrees C, and it's moving with a velocity of u infinity, which is 8.1 meters per second. And this hydrogen flows over top of whatever shape thing this is. We need the surface temperature to be minus 15 degrees. But we want to know in this kind of weird, goofy situation, I don't know what we're designing here, something. So we want to know Q. We want to know the heat transfer. So how we could do that, we could do some calculations and predict it. Those calculations would have some errors in them. So we may not actually be able to get a super accurate result. So another thing that we could do is we could take a step back and say, instead of doing a calculation to predict it, we could do an experiment and measure it. If we look at this situation, some experiments are fairly easy to do, fairly straightforward. This experiment, we're doing it at elevated pressure, which is probably fine. We're doing it at low temperature, which is potentially not problematic, but it would be a little bit challenging in terms of designing the setup. And we're doing it with pure hydrogen, which is probably the most problematic thing for this specific setup. So some experiments are difficult or dangerous or expensive, or there's some other thing that is limiting you going out and actually doing the measurement that you want to do. So the question that we're going to ask is, can we do a similar experiment? And I'm going to underline the word similar because this is really the key concept here, right? We're talking about, so you can see at the top, similarity. So what is a similar experiment? If we think back to what's happening, physics is happening, as physics tends to do. Physics is happening. The different physical laws or physical equations that we've talked about, which are governing the fluid flow and the heat transfer in this situation, are conservation of mass, Newton's second law, conservation of energy. So these are really what is governing the physics of the system. These are the important equations, and yikes. And from a heat transfer perspective, what we're interested in is the heat transfer at the surface, Q double prime sub S, Q heat transfer at the surface. So this is surface heat flux. The surface heat flux we know from before is equal to, one way to talk about it is conduction through that first layer of fluid, right? This is conduction through fluid at surface, through that stagnant layer of fluid that's right at the surface. And what we did before was we non-dimensionalized this equation and got to this equation, where our dimensionless temperature gradient, dt star dy star, is equal to y star 0. That should be y star. Okay, so what can we conclude from all of this? And I'll expand my screen a little bit so we can see all of these equations. These four things, conservation of mass, Newton's second law, conservation of energy, and then the surface heat flux, those are the things that we care about. And if we look at all of these equations, we could go through and solve them. We're not going to do that because we can't actually solve all of these explicitly. But if we went and looked, we could see this top equation just depends on these dimensionless variables, u star, x star, v star, y star. This second equation, Newton's second law, depends, the only constant in it is the Reynolds number. Conservation of energy has only two constants in it. It has the Reynolds number and the Prandtl number. And then the heat transfer problem down here has only the Nusselt number. So what can we conclude from this? The physics depends only on Reynolds and Prandtl. Right, that's these three equations here at the top. Should have written that in blue, but so it goes. So the physics depends only on Reynolds and Prandtl because those are the only constants here and here in any of those three equations. And the heat transfer is characterized by the Nusselt number. So these three are all that we really need to care about: the Reynolds number, the Prandtl number, and the Nusselt number. So let's think of a test system. So our task over here, design a test system at ambient conditions. So we want to be able to predict what the heat transfer is in this real system up here, but we want to do our actual test under ambient conditions in 1 atmosphere of pressure, 23 degrees Celsius. So what our strategy is going to be is to make if the Reynolds number, if this is true, if the Reynolds numbers are the same and the Prandtl numbers are the same, then the Nusselt numbers are the same. So this is the strategy of similarity. We can look at the fundamental physics and say that these are the three things that are important, and if we can make the Reynolds number and the Prandtl number the same, then the fluid flow and the conservation of energy aspects are the same in our real case and our test case, in which case the heat transfer part of the problem must be the same. The Nusselt numbers must also be the same. So our three dimensionless groups, Reynolds number, which is the velocity times a characteristic length, in this case, that would be the length of from the front to the back of whatever shape we have, divided by the kinematic viscosity, nu. The Prandtl number is the kinematic viscosity over the thermal diffusivity. Another way of thinking about it is like how momentum diffuses through the fluid by viscosity, and how on the bottom how heat diffuses through the fluid by conduction. Another way to write that is heat capacity times the viscosity divided by the thermal conductivity, K. Then the last thing, which looks kind of like a BO number but isn't, is the Nusselt number, which is H, which is the convection coefficient, right? H that we've normally used when we've been modeling convection, times L, which is this same characteristic length that we saw over here, divided by K of the fluid. So these are going to be the three things that we care about. We're going to pick conditions where the Reynolds numbers are the same and the Prandtl numbers are the same, and that will give us Nusselt numbers, which are the same. So if we think of, we're going to need different fluid properties like kinematic viscosity and thermal diffusivity and Prandtl number and all of these different things. So these are all temperature dependent properties. So we're going to find our fluid properties at two average temperatures. So we're going to find it, right, the temperatures in our real system are hydrogen. So this is the real system. We have hydrogen. Our test system, we have air. In our test system, we know we measure TS equals 30 degrees Celsius. Let me just make that blue so that we can see it a little better. TS equals 30 degrees Celsius, and we measure QS double prime. So measuring heat transfer is typically not terribly difficult. So we'll say this is TQ prime air is equal to 50 watts per meter. Okay, so this is this here and this here are experimental values. We don't know yet what the velocity of the air should be, but we'll figure that out soon. Okay, so these are, we're going to look at the properties of hydrogen at 250 Kelvin, and we're going to look at the properties of air at 300 Kelvin. Just so happens, if we look in our book, this is from the back of our book, we can find properties for hydrogen at 1 atmosphere and air at 1 atmosphere. Hydrogen, we're not actually at 1 atmosphere, we're at 2 atmospheres. But we can look in our book and find the Prandtl number, the kinematic viscosity, the thermal conductivity. We can find other things like the normal viscosity. We won't actually need that right now, but we could find it. Lo and behold, our Prandtl numbers are the same. And the good thing is, right, so we chose conditions, we chose fluids and conditions where we have approximately equal Prandtl numbers. Right, the Prandtl number of hydrogen is equal to the Prandtl number of air. The Prandtl number is the heat capacity times the viscosity divided by the thermal conductivity. It's going to be approximately independent with pressure. Not exactly, but approximately. So we can say that, right, we've kind of checked this box where we have the Prandtl numbers the same. Now remember, we had to make the Prandtl numbers the same and the Reynolds numbers the same, and that would make our Nusselt numbers the same. So now we need to find conditions where the two Reynolds numbers are the same. So our Reynolds numbers, right, if we want to make the Reynolds number of our real system with hydrogen equal to the Reynolds number of our test system with air, we need this to be true, this equation here. Right, the velocity of our hydrogen times the length scale in our hydrogen case divided by the kinematic viscosity of hydrogen equals the same stuff for air. We can rearrange that equation and just move some stuff around and solve for the velocity of our air. Now the problem is what we looked up. So we looked up the kinematic viscosity for hydrogen at 1 atmosphere. Remember, kinematic viscosity equals the viscosity divided by the density. So density is not constant with pressure for gases. It is for liquids, but not for gases. So if we have a gas, what we looked up from before is we looked up the kinematic viscosity of hydrogen at 1 atmosphere. We found it was 81.4 times 10 to the minus 6 meters squared per second. We know that the kinematic viscosity equals the viscosity divided by the density. And we know that PV equals RT, or P times 1 over the density equals RT. So density equals P divided by RT. Okay, so we can put these together. Sorry. And basically look at how kinematic viscosity, this is that's specific volume here, just to not be confused. This is kinematic viscosity. So most of our little script V's have been kinematic viscosity. Just this one is specific volume. Sorry, lots of V's. So the kinematic viscosity, well, the ratios of our kinematic viscosity, V1 divided by V2, is equal to P2 divided by P1. That's because our density is proportional to pressure. So our kinematic viscosity is inversely proportional to pressure. That's what this is saying here. So we can use this equation here and solving for V2, this, so V2 equals 81.4 times 10 to the minus 6 meters squared per second. Okay, sorry, I'm finding mistakes in my notes. So I did this wrong. It should be, if I use this equation correctly, it should be times P1 divided by P2. All right, so then this would be times 1 atmosphere divided by 2 atmospheres. So the pressure on the top where we got this number over here, 81.4, divided by the pressure that we care about, 2 atmospheres. So our kinematic viscosity in our real case is 40.7 times 10 to the minus 6 meters squared per second. All right, then we simply have to plug some of these values into this equation here to get the Reynolds numbers to line up. So that's what we're doing here. We're plugging in the velocity, the length, kinematic viscosity, so the kinematic viscosity of air, 15.89, the length, and then the kinematic viscosity of hydrogen, and that gives us what our velocity of air would need to be. This is the velocity of air needed for the Reynolds number of the hydrogen case to be equal to the Reynolds number for air. So in our test case, for that to be similar, for the dynamics to be the same, for the physics to be the same, this is the speed that the air would have to flow. What similarity says is, since these are the same and these are the same, then these must also be the same. So we can write, that's what we're doing down here. We can write that the Nusselt number of our hydrogen, that's going to be equal to the average convection coefficient. This is average convection coefficient. Average convection coefficient. Technically, these would be average Nusselt numbers. Average Nusselt numbers. We can find the average convection coefficient really easily if we have experimental data. So this guy, P, this is the object perimeter. Okay, right, like, okay, so that's h bar of the air times the temperature difference. So this is the surface temperature that we measured in air, T infinity of air, and we can go through just like how you might expect, and we can get a value for h bar. This would be 47.6 watts per meter squared Kelvin. So this is an experimental value that we can measure. The good thing is, since the two systems are similar, we'll calculate over here the Nusselt number of air, so HL over K. That gives us this unitless number, 109.8. That's the Nusselt number. And again, because the Reynolds numbers are the same, the Prandtl numbers are the same, the Nusselt numbers are the same. So the Nusselt number of hydrogen must also be 109.8. We can plug in the knowns that we have, what L is, what K is, and we can find what H is. So this is a nice experimental way to determine systems that are otherwise kind of complicated or challenging to do experimentally. We can design a similar system. It's not always easy, but we can spend some time and pick the right fluid and pick the right conditions where we can get similar Reynolds number, we can get the same Reynolds number, the same Prandtl number. Then we can do an experiment on that system and use the Nusselt number to kind of connect the heat transfer happening in one case to the heat transfer happening in the case that we actually care about. So kind of a cool process. We'll use some of the ideas from this, the Reynolds number, the Prandtl number, and the Nusselt number to to begin to extend some of our other models into different empirical models. And we'll do that kind of as we continue to explore convection.